So today's lesson is going to be over intermolecular forces, which is the forces between the molecules. So far, what we've been talking about in bonding is the bonds between two atoms. So we have ionic, which are the strongest, covalent, which of course share electrons, and then lastly metallic. So metallic bonds we don't talk a lot about. That's where you have the sea of electrons, and their strength is kind of hard to compare to the other ones because they're different types of bonds. So I just want to make sure you understand that this next lesson is not the bonds between the atoms, it's between one molecule to the next molecule. So intermolecular forces, and of course if we're talking molecular forces, we're going to be talking about covalent compounds, are the forces of attraction between the molecules, okay? They vary in strength, but they are weaker than the bonds that join the atoms together. Intermolecular forces, we call them IMFs for short, are only between covalent compounds. Because remember, your ionic compounds is a network of positive, negative, positive, negative, positive, negative. So that's what's holding an entire ionic compound together. But in the case of a molecule, we have to have something that holds one molecule to another molecule. In other words, why is water liquid? Because something is holding one molecule of water to another molecule of water, and etc. Same thing with why can we make ice out of it. Again, we've got to have something that's holding the molecules or binding those molecules to each other. And so that's what we're going to be talking today. The strongest of the intermolecular forces are going to exist between polar molecules. And remember that polar molecules are molecules that have an uneven distribution, or they are not shared equally, of that electron. So we create those dipoles, where you have a slightly positive end and a slightly negative end because of them not sharing the electron equally. So their first kind we're going to talk about is called dipole-dipole forces. And that is when the positive end of one dipole is attracted to the negative end. Remember, those are the slightly positive. We did that little, sorry about that. We did that little delta symbol, delta positive, delta negative. So they're not full out charges, but they're slightly positive, slightly negative. So opposites attract, so the slightly positive end is attracted to the slightly negative end of the neighboring molecule. So the dipoles, remember, are the equal but opposite charges that are separated by that short distance, and they are caused by the unequal sharing of electrons. So it kind of looks like this. So we have an HCl, which is definitely a covalent molecule, definitely polar covalent. So we have that slightly positive end being attracted to the slightly negative end. And the way that we will show if it's a IMF or an intermolecular is we show it by this dashed line right here. Excuse me. We show it by the dashed line because it's not a full out bond like the one that's here between hydrogen and chlorine. So we could draw a whole series of this, because then we could say we have an HCl down here, and we could show a bond here and a bond here, an IMF or a dipole force. Okay? So that is dipole-dipole. Also remember, we could show that bond like that sometimes. So then this would be attracted this way too. So you could see that this slightly positive end would be attracted to this slightly negative end. Hydrogen bonding is a type of dipole-dipole. So let's write that down, type of dipole-dipole. But it's actually stronger, it's the strongest of the intermolecular forces. And it is when you have hydrogen, so it's called hydrogen bonding, so you've got to have hydrogen, and it's bonded to a highly electronegative atom. It's attracted to the lone pairs on that electronegative atom on the nearby molecule. They are the strongest, so make sure you know that. So they are the strongest of the IMFs. It is responsible for the high boiling point of water, okay? And there's only 3 elements that will hydrogen bond, and that is nitrogen, oxygen, and fluorine. And I came up with this a long time ago. I remember it by No Orange Friends, okay? So Giga-Maggies, all right? So this is kind of what this looks like. So instead of being attracted to, it's still a slightly positive, slightly negative, but because of those lone pairs on those highly electronegative atoms, it's attracted even stronger, okay? So this would be an example of hydrogen bonding, okay? Hydrogen bonding gives things a higher boiling point than they should have, because normally when you go down a group, for instance, if we look at group 16, that's where oxygen is located, right underneath it is sulfur, and you can have hydrogen sulfide. Normally as you go down, your boiling points get higher as you get more atoms, but water has a higher boiling point than expected for that trend because of the hydrogen bonding, because those bonds are harder to break. That's why it takes water a lot longer to evaporate than, say, alcohol. Like if you have rubbing alcohol, evaporates really quick, but water takes a lot longer to evaporate. So it gives that higher boiling point, and there's actually a lot of qualities that water has, and it's because of the hydrogen bonding, and it's a stronger intermolecular force to overcome. The third kind we're going to look at is called London dispersion forces. Sometimes we'll call those LDFs for short. And the London dispersion forces are very weak. They're the weakest of the IMFs. They result from the constant motion of electrons and the creation of instantaneous dipoles. And what I mean by instantaneous dipoles is they're created and then they disappear. And they do this over and over. And it's because as these molecules are moving around, not these molecules, excuse me, the electrons, as they're moving around incredibly fast around the nucleus, they're creating these instantaneous dipoles where it's there and it's gone, it's there and it's gone. So the overall effect is that it doesn't have a charge, but it's still enough while it's there and gone, that there is an attraction. They act on all molecules. Okay, so everything has London dispersion forces. When we're talking about polar molecules, though, they're there, but they're not strong enough to worry about, because the dipole-dipole or the hydrogen bonding is so much stronger that that's going to be what's affecting the behavior of those compounds. But they are the only ones that act upon nonpolar molecules. So if you have your Brinkelhoffs, you've got fluorine, chlorine, bromine, etc., hydrogen, those are all nonpolar molecules, but they do have these London dispersion forces, okay? If you look at the group 17, which is the halogens, the LDFs get stronger as you get to be a bigger molecule. And the reason for that is because you're getting more and more electrons, so you're creating a little bit stronger dipoles. So that explains why, if you look at group 17, fluorine and chlorine are gases at room temperature. You get to bromine, and now you're a liquid, which that indicates stronger LDFs because you're able to form a liquid. And then iodine would have the strongest of those London dispersion because it's the biggest and it's a solid. And so without the having London dispersion forces, none of your gases could be liquefied. So we couldn't get liquid nitrogen, which you're familiar with, if there wasn't some London dispersion forces there to be able to, as you get enough pressure and get it cold enough, you get the molecules close enough to each other, they will liquefy. Okay, same thing with the noble gases. They still have London dispersion. Of course, they're not as strong because of the noble gases, but you actually can have liquid argon if you get it cold enough and enough pressure. And so that's what London dispersion forces are. Okay. So here is an example of what that looks like. The electron cloud gets a little bit off balance, and there's that slight attraction. But they are very temporary because, like I said, it's there and it's gone. It's there and it's gone. But they are the only ones, I want to make sure you understand that. They're the only forces that act upon nonpolar, and as you get a bigger molecule, the London dispersion forces get a little bit bigger as you get bigger, but then they act on all of the molecules. So polar also has London dispersion forces, but it's not as strong of an effect as the dipole-dipole or the hydrogen bonding. So what are these effects on these intermolecular forces on the states of matter? Okay, so here we have gases. You have a low density, easy to expand or compress, and then it's, of course, gases fill the container, and it's the weakest of the intermolecular forces. So if you have a gas, your intermolecular forces are very weak. Okay, as you get a little bit stronger, or we call it intermediate intermolecular force, then you start getting liquids, and you have a higher density. Of course, liquids are hard to expand or compress, and then, of course, they take the shape of the container. And then the strongest of the intermolecular forces are going to be in solids, because there you have a high density, hard to expand or compress, and they have that rigid shape because they have the strongest of the intermolecular forces. Okay, so continuing on with that, intermolecular forces. I think your notes say interparticle forces, so you probably need to drop that off and say intermolecular forces. They're responsible for properties such as flow rate or viscosity. If you remember from probably 7th or 8th grade science, viscosity is the resistance to flow, or how thick a liquid is. So like maple syrup is much more viscous than, say, water. Okay. They're also responsible, especially in water, for surface tension. And surface tension, remember, is when the molecules on the surface pull closer together. That's why bugs or leaves can float on top of the pond. Melting point and boiling point are also higher if you have higher or stronger intermolecular forces. And then the vapor pressure of a gas, which vapor pressure is how readily will a liquid become a gas. So, for instance, water has a fairly low vapor pressure, but say gasoline has a very high vapor pressure. Again, stronger the force, the lower the vapor pressure. So hydrogen bonding is very strong in water, so it has a lower vapor pressure. Whereas, say, in rubbing alcohol, it has a much lower intermolecular force, so it has a higher vapor pressure, meaning it becomes a liquid very easily. So let's just see what we know here. Arrange the following in order of which will vaporize more quickly at room temperature. Okay, so take a second and try to figure that out, and then we will tell you the order. All right, so in order of more quickly, you're going to have B, then C, sorry, just about that, and then A. So water would be the slowest to evaporate, and acetone would be the quickest, and then, of course, alcohol would be right in the middle. Okay, so this chart got left out of your notes, and so I want you to pause the video here, and on the back of your notes, you need to write this chart in. Okay, so basically what this chart was doing is telling you, summarizing what we've been talking about as far as the bonds between molecules. It just got left out, but it's going to be a useful study. Not between molecules, I said that wrong. Between atoms, sorry. It's early and I am not with it this morning. So here we have the type of bond formation, type of structure, physical state, melting point, solubility or soluble in water. And I showed you this chart after we did the lab, unless your first period, I forgot. But I remember I gave you that treat to make up for it. But please write this down so it'll help you study for the test. And then once you're done, stop the video and you can start on your worksheet.